loop resemblance. All right. So as we know, the grid synchronization is more the researchers or the industry that tends to apply best lock loop. All right. As we know, there's alternative methods in order to do that. All right. So this research focus on the second method. All right. So let's we go through the first slide. So this is our tentative or the flow for this sharing. Right, the first part I would like to talk about more on the state of the art of the best lock loop itself, as well as droop control. All right, because why we choose droops, we will see it further. I will discuss it later. All right, and then we will see what is the resemblance that we can tell about. And lastly, we see the performance. All right, for the performance, frankly speaking, all right, we just see the result based on the simulations. MATLAB. All right, why, if you ask why only simulations, because to be honest, this so-called microgrid concept, all right, since this research is focused more on the microgrid concept, so meaning that it's involved with the RE, renewable energy. So our government policy is not that more towards to the government, to the renewable energy yet for now, but I believe there's a stepstone for it, right? So yeah, that's why we only focus on the MATLAB, sorry, the simulation results. All right. And all right, so this research is basically based on the, as I said, microgrid applications. So what is the microgrid? I believe some of the audience is not familiar with that term, right? So microgrid is basically a mix of, distributed generation, for example, like solar, wind turbine, as well as you name it, all these renewable energy, right? But in Malaysia, we only famous with the hydroelectric, right? Seldom we hear about solar or, I mean, the huge plant, solar or wind turbine. All right, so basically these microgrid concepts already applied or utilized by the EU, European Union, right? The first player is Denmark. All right, they use this microgrid in a good manner. All right, so this is the overview of that concept. All right, so in order to to connect or sync, to have a linkage between these components, we need a controller, or we need a so-called main controller, either centralized or decentralized. All right. So one of the controller is that grid synchronizations. So meaning that's how we connect our system, all right, our power system with grid, as well as how to isolate from the grid. So yeah, this is our focus to see the technique of these grid synchronizations. All right, so we will see what the difference between the best lock loop as well as droop control. Why we choose droop rather than use the normal way best lock loop. Okay, so basically the best lock loop is formed, or amongst the research world back to 1932, right? Basically used in telecom as well as radio and inverter to do some analysis. And based on some research that we did, we found that more than 20,000 papers regarding the best slope synchronizations or a technique, while through the using a droop control only less than 1,000 papers. So meaning that there's a more, we can do more exploration for using this droop control. Okay, we will see what is the resemblance between why we choose droop in terms of for this technique. So before we go further, we would like to see what is the advantages as well as drawbacks of this synchronization techniques. We just focus on the PLL, all right? So yeah, you can find this review through our paper, all right? I will share it later. So please go for it, read and cite it. Just kidding. All right, so the PLL I believe for the advantages is why the resistor more use this, because it provide good estimation as well, accurate test log. All right. So the implementations or the design is quite simple, straightforward. We'll see how it's done. However, of course, everything have a drawbacks, right? So one of it is best of slope is not that really, I wouldn't say not really, but vulnerable in high grid fault, meaning that for the unbalanced conditions. All right, due to the computational pattern in the PLL itself. Okay. And yes, this is the overview for the basics PLL concept or configurations. All right. So we have three main components. The first one is a test detector. All right. PD is not a port Dixon, test detector. All right. We have a LF or low pass filter, and we have VCO, voltage oscillator, or a voltage control oscillator. So PD or phase detector is basically used to detect the error. Of course, for the controller, we use error for our reference, right? So this PD is basically to multiplier or to multiply our error, and it will inject it to the low pass filter, that is to extract the DC components. All right, basically for the controller is you know, work or coordinated with DC components, not involved with AC. So everything we need to convert to DC first. And lastly, we have a PI. We're using PI, that is a professional integral. This is the basic one. Of course, nowadays we have difference. We have SOCI, even use PR, professional resonant, and some use PID in order to generate the to induce phase signal, right, from the frequency. Okay. All right. So this is the state of art for the droop control. All right. For the droop control, if you see that we have like almost, I would say 70% similar with the best of loop configurations. Why? Because we have voltage as well as current signal for our reference. All right. So from this voltage and reference, we will use so-called block transformations. Either we use Bach or we use clock. That this meaning that we use alpha beta or we use DQ. It depends on the applications. But for this case, this is just we use DQ transformations. So as I said, we just use DC. If you use alpha beta, it's more like AC. All right. So the first part is to generate our power equations. All right. Since droop is basically adapt from the droop from the synchronous generator, right? Because in synchronous generator AC, right, we use droop, meaning that when the frequency is increased, basically our power, our rated power is decreasing, and vice versa. All right, so the advantages for this droop, you can see that it does not require, there's no requirement for the central controller. So meaning that we can independent regulate this droop control. So that's why the first point is local measurements. We only use the parameters from the wherever that's been injected. All right, so that's the good reason for it. Number two is no communication network requires, meaning that we will not use any bandwidth. All right, so we don't have like to have something to inject it, meaning that we need the assistant, all right, or command. And lastly, simple designs. I won't say like simple, but it's easy to, not easy, it's quite impossible to implement. All right. However, the advantages for droop is that I say is more towards the power sharing from our, since this concept is using synchronous generator. So we will try to overcome these disadvantages, all right, no synchronous functions. So from that, we try to resemble what we can use or compare with the current synchronization technique, that is a PLL. All right. So after we done some this and that, after some reading, review and all the sorts of thing, and then we find that actually we trying to prove that the droop control or droop technique is we try to prove it. We can use this technique for the synchronization mechanisms. All right. So for example, like patch lock loop, you can see the first red blocks over there. All right. Once the reference pass through the VCO, we can see that it can extract the phase, right? That is from the frequency. So we use integral to convert, all right, this frequency or output frequency to become our reference phase. Same things with our droop, all right. If you see our droop, all right, we have a frequency equation actually. You can see the second, you can see from the figure B, the red block there, all right. You can see that our frequency is something that we can supply, meaning that we can eject these reference values and compare with our real power or active power, where this power is, as said, is from the droop, conventional droop equations. Okay. And from there, we can generate this, we put same technique, we put the integral and we can extract the phase. So in order to test that, we will try to produce, or not produce, we introduce the virtual current. You can see from the figure below, all right? We introduce the virtual function. So meaning that in order to test that, before we directly connect our power system, our isolated microgrid to the grid, we need to have something in order to test that either that our system is really wanna sync with our grid. All right, that's why these virtual functions come, right? So basically for these functions, all right, when the current grid is 0, the inverter state is, as I said, still in isolated mode, and the position for the switch is from 1, all right, to be in position 1. When the inverter voltage is successfully synchronized, meaning that the phase from our droop is matched or locked with our grid, our fundamental frequency of phase, then the circuit breaker, so-called circuit breaker, will be turned from 1 to 2. All right, so meaning that our system is ready 100% wanted to connect with grid, right? So this is the setup for simulations or doing these pieces to this pieces. Okay. So basically, as I say, we use a path transformation. It's a D&Q. We convert AC to DC signal first, and then from that we can do more control. I mean, if we use DC, it's more applicable compared to the AC. All right. So the first part is signal transformations. Okay. After that, this signal transformation we check with our reference. That is a virtual function. All right. And you can see that after that, it will go through the virtual impedance. That is our virtual functions. And if our system is ready to meet with our grid requirement, and then we just switch from 1 to 2, or either 1 to 2 or 2 to 1, depend on the requirement. All right. So after that, it will go to the power calculations, and we will get our reference for reactive as well as active power. And then after that, we just use signal generator in order to get our phase or induced voltage reference. Okay. So this is the parameters that we use, and I believe this parameter is not as simply put there or simply try and error. All right. We use equations before we use. Before we introduce this value, we use some equations in order to test that, and then we have published this paper regarding these parameters for the inverter. So meaning that this parameter is being, recognized by other people, isn't it? Internal, right? So, and of course, this is our results in terms of the. So you can see that the purple color is droop as well, while the blue color is for the PLL. All right, so we can see that the droop is can mimic the PLL performance. All right, so meaning that yeah, we able to prove that this droop can be invite to become a synchronization family. So yeah, the research is still going on to to see how. And in fact, nowadays we have a so-called synchron inverter. All right, so meaning that this inverter will be without any dedicated synchronization unit. It just use the synchron inverter, and then it will directly sync with the grid. And then that is not our scope lah. All right, so let's see when we want to try. All right, let's see what is the result when we put the function, the virtual function. All right, so as we see that from figure A, this is our reference. All right, so meaning that our troop able to resemble, to mimic the V out equivalence to the VG. All right, VG is a voltage grid, and V out is from our inverter. This is from our power system. Inverter meaning that from DC to AC, since our sources is like renewable energy, right? Power like solar, wind. So we are converted to AC first. That's why we use inverter, power converter, right? So you can see that at 0.12 seconds, and also this is not limited to 0.1 seconds. All right, this is based on our data. All right, so synchronization is activated, all right, at this time, at this point, at 0.12 seconds. So without any delay or any further tensions, we can see that our synchronization mechanisms can sync, all right, able to sync our reference from the power system with our fundamental signal is from our grid. Okay, and then this is of course we need to check the voltage as well as the current. All right, and the voltage is, you can see that 3 to 5, that is peak to peak value, and of course for the VRMS like 155 or 230. Right, and yeah, it's a perfect result, guys, because as I said, this is a simulation, so simulation is perfectly perfect data, right? So all right, as you can see that our voltage and current is steady, in a steady mode. All right, there's no although during the balance conditions. All right, so we can see that we have a small hiccup for the frequency as well as for our power. Since our power and frequency is inverse proportional, so when the power is dropped and the frequency is high, while the frequency is high, our power is slightly increased. Okay. And lastly, I would say that not only to test our synchronization mechanism, but we need to test the frequency restoration as well. So using this droop, since droop already have its on frequency function, so we need to enhance this frequency function in order to able to restore our frequency when we're having grid failure, or for example like blackout, as well as unbalanced conditions in terms of like maybe heavy load. So using this test, this frequency restorations, we able to restore our frequencies to maintain with our standard, that is a 50 hertz, right? The maximums, minimum and maximum for the tolerance is plus minus 5%. Is standard for it. Okay, from the result, we can see that it's able to maintain the frequency when it have minor turbulence, let's say. Okay. And yeah, I think we almost reached to the finishing line. All right. So for the conclusion is that we're able to prove that the droop technique is we can say 70% able to mimic or can become a synchronization family. So with further enhancements, further research, we can say that droop is 100% can become a synchronization. Not only synchronization, but at the same time, it can share the power. For patch lock loop, one of the limitations that it cannot share the power. All right. I will not, don't get me wrong, it's not share the power, but it needs further improvement as well. All right, that's why we select this alternative method rather than just only use conventional. All right. I think that's all. So as I said, I would like to promote our paper. So this is our paper regarding to this research. So hopefully you can have go through and read it during your free time, lunchtime, dinner time, or before you go to bed. And this is regarding this paper is for your reference for the literature review. What is the technique that synchronization techniques for the microgrids or for the power systems? For the isolated power systems. I would like to share you a story. Back to 2017, we have a visit to Sepang, KLIA. All right, KLIA using their own systems, meaning that they use their own electricity supplies. So meaning that they have, because the electricity come from solar. Yeah, KLIA the first panel using this so-called microgrid systems. However, they share that they're able to save the electricity in terms of investment. All right. So even when they have the extra power, all right, when they have excess power, they can share, not shares, they can they can share the power to the TNB, meaning that they inject that extra power, is extra electricity to the TNB. Because even our government provide the so-called this tariff when you have extra power, all right, we can sell to the TNB. Yeah, we can sell it to the TNB. So in our country, the system is moving slowly, and now it's I think everyone know about these systems. But of course, the capital for this investment is high. All right, I think that's all for my sharing. Thank you for the audience. All right, to the master and to the moderator. Hopefully, you guys can get some input from this boring sharing, right? All right, over to you, Dr. Sazmi.
Okay, thank you very much, Dr. Ronald, for your great sharing. Now I open the floor to others to ask any question regarding our speaker talks. And if there is no questions, now we have come to the end of the session. And thank you very much for your participation and attention. And thank you all, and see you next time. With that, I thank you.
All right. Thank you, Dr. Sazmi. See you, and thank you, Dr. Anissa, right?